not when I'm recording because they can't see or hear your answers. So, local linearization, what's it used for, and what's the theory behind it before I give you a formula for it. So I gotta go use my smartboard's been, oh, there it is, been very finicky today. So just watch up here and don't write anything down, and I'll tell you sort of the theory behind what you're gonna do. There will be a function. You may or may not know the expression for it. So it might say f of x equals x cubed minus 3x plus 4, maybe, or it might not. Either way, there's going to be a function presented to you, and I'll just make a fake one, and I won't, in this situation, tell you what it is. All right? What you're going to do is hop on the function at a particular spot. In the model for it, they're going to call that spot c, f of c. But I think variables are kind of funky to work with, so I'm going to make it very specific. I'm going to say, suppose this is at 2, and this is at 2, 4. And I'm going to hop right on there. Nothing hard about that, correct? You'll have a point, and it'll be that point of tangency that we've been working with a lot of our derivatives. You are going to write the equation for the tangent line to the curve at that point. So again, still not, I'm going to try to make it so that nothing is new, even though it's a new concept. That is not new, hopping on a tangent line, right? What two things do we need to write the equation for that red line? Because you still need them today. We're just going to be applying it a little differently. I need the slope and the point. So you'll either be given the point, or if they only give you the x, then they have to tell you the model for the curve for you to plug it in and get the y, just like always. So you have to have that point, and then you guys also said the slope. And in this class, how do we get the slope of a line when we only have one point? Up until calculus, you couldn't do that. They had to give you two. But with calculus, you can find the slope if you know the derivative. Exactly. So you're going to calculate the derivative at that point. Let's say this one ended up being, I don't know, 3/2, right? So you have your point and you have your slope, and I'm going to have you not do anything new. I'm just going to have you write point-slope form for the equation of this line. I want you to still think of it like you did in Algebra 2 and in pre-calc and in here. Just go y minus the y you know is equal to the slope there, which is now called the derivative, times x minus the x you know. That will not change. That's the equation for the red line, but now you're going to use it. That's the only difference. We've already been writing them. Now they're going to say use it to approximate what the value of, and they'll stay very close to the point of tangency. So they'll say use it to approximate the value of 2.2. Because if I go over to 2.2 and hop on the curve, I have no model to plug it into, right? I can't find it, because I don't know what's making all the black points that are making the black curve. But if I plug 2.2 into the lines equation, I'll get a value. And do you see how that value, that little gap between those two dots, is very small? You see how it's a very small window of error? There will be some error because unless you're at the point of tangency, there's a gap between my line and my curve. But as long as you stay close to the point of tangency, so when you do this, you'll always be really close to the point that they give you. So if they say you're going to do the tangent line at 3, guess where you'll be making your approximations? Really close to 3. They won't say go out to 5. Here's why. It's very, 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 very bad approximation as I move farther away. If I say approximate what happens at 5, do you see the huge gap between my line and my curve? Like, it's huge. So I'm going to tell you, you're going to learn a very, very weak method for approximating. Now, she's in Calc 2 and just took a test last week on Euler's method, right, my dear? And she had to not stay on this line forever. We kept tweaking it, right, Abby? So she would hop on this line for a little bit, and then we'd say, stop, change your slope, and head out. And then we'd say, stop, change your slope. So you would actually change your slope and not do it. You can go, Abs. She's standing there. She can ask me more. Which is far more accurate than heading on this straight, rigid, constant sloped line, right? So I'm going to tell you it's a very weak way to approximate what happens on a curve unless you stay very close to the point of tangency. All right, so how is it going to change from what you've been doing? You're still going to do this, which we know how to do, right, Connor? Here's where it's going to change. Very easy changes. You're now going to solve it for y. You know how I've always said, just leave it. You're not. You're going to solve it for y, Nate, but it's pretty easy to move a -4 over, so that shouldn't stress you out at all today. All right, so you're going to solve it for y, and you're going to leave it like this. Then you're going to rename it, because these are called tangent line approximations. So some books call it a function called t of x. Our book, I think, calls it L of x. I don't really care, but if it's not multiple choice, I'd like you to rename it. Christian, if it's multiple choice, no one would know you did anyway, so don't do it. All right, so I can approximate what happens on the curve by using this red line. So how does it work? You go like this. If I want to know what happens at 2.2, I'm going to approximate it. Again, we're not taking any notes yet because I just want you to see it. Is it making sense, Paige? I'm just going to say, well, I'm going to hop on the line. How do I hop on the line? I put it into my linear approximation. I just go throw a 2.2 in and see, well, what is the y value there? Correct? And it becomes some work with decimals, but you should be okay. It'd be 4 plus 3/2 times 2/10, right? 2.2 minus 2, so these would cancel. So 4.3 would be my estimate, correct? Then again, I said there's a few differences. Nothing here is new, except we moved a 4 over, which we normally didn't do, and we actually used the line when we were done. Make sense? So look, this is what I just found, that this is at 4.3. This is the actual value on the function. So I'm a little too what? My approximation is a little too high. There's a calculus reason for that, and you're going to have to know what it is. It's too high because my tangent line is above the curve. But if I had been over here using this to approximate, over here on this line to approximate what happens at 5.1, then I still have this little gap, but my line's a little low because it lies below the curve. So what calculus do you think you'll be doing to decide if you have over or under estimates? What causes tangent lines to be above a curve versus below? Yes, concavity does. Yeah, so you have to know how to figure out the concavity in that area. And then what calculus do we do for concavity? Second derivative, right? If it's greater than 0 in this region, we're concave up, so our line will give us underestimates. If we're less than 0, we're concave down, so no matter where we are, our line's always sitting above the curve, so we're a little over. That's generally what you're doing. Do you think you'd be able to pick it up pretty quick? Because I would love to cut the notes not to that full sheet. So I think what I'm going to do is we're going to hop in the notes kind of midway. I'm going to go back here. So I showed you the concept of it before I gave you this formula, because I'm going to tell you when I first started teaching this, I launched right into this stuff right here, and kids were fine on the homework, but within a few days they completely forgot how to do it. So if you were to Google this topic, this is what it would say for local linearization. It would have a little graph, so go ahead and make one. So now we can start writing. There'd be a little thing here, but it wouldn't be a specific like we did. It'd be generic. They'll usually call the x-coordinate C or A, so I'm going to call it C. And there'll be a little picture where somebody, the author, will have been hopping on the curve. So unlike my last one where I called it 2, 5, generically this is called C, F of C. So same thought process though. And then what we're going to do is we're going to hop on it with a tangent line. What did I say we're going to call our line? What do we call it? T of x for tangent line. So it's not f of x. We're going to call the curve is f of x. The line we're going to call the tangent line or the linear approximation line. That depends on books and teachers. And we're going to use this. So we're going to say used to estimate. These are approximations. Values of a function using tangent line at C, f of C. And then what you would see is a model that looks like this. There won't be any numbers like I just showed you, but it's the same thought process. There'll be a T of x equals, or an L of x. It's going to say f of C. Understand why. Remember how it was y minus the y you know? Wasn't the y I knew the f of C? So this is getting added over. So in the model, it gets added over, plus the slope there, so you'd see an f prime of c, times x minus the x you know. This is what you would see in a textbook or if you Googled tangent line approximations. I'm going to tell you to put it in a box, and I'm going to tell you to really avoid using what's in this box. I really just want you to create it with stuff you already know because it's already in your brain. So then you don't have to memorize this model. Like I said, I used to start it like this, and this is what kids would do. In their homework, this would be a 2, 7. So they go C, I put the 2 here. 7, I'll put that here. But they didn't know why they were putting it where they were putting it or what they were doing. So guess what happened, Paige? A week later, what happened? They had no clue how to do it anymore because they didn't really understand it. So I'm going to write avoid. I'm going to write just use algebra 2, point slope form of a line. So we're going to use our algebra 2 plus the fact that we know how to write tangent lines, plus some good arithmetic, and I think we'll be really successful. So let's write good arithmetic. And I think we can avoid the calculus model for this. We're going to go try one right off the bat. All right, I think we're on the back side of your notes because the front side I tried to do without you writing. So go ahead and take a look at this. We've got some function. I have no clue what it is. Now in number 2, I told you what it is. So the problem's changed, but the process won't. And now that they've changed it to G, if you understand it, it shouldn't matter that the model has F. So let's go take a look. It has F of 2 equaling negative 6. There's your point. So remember, it's all about a point and a slope. It's easy if you just think of stuff you already know, Allison. And it says, I'm going to give you the slope as 5x over y squared. What is that? What is that? When it says the slope, it's the what? It's the derivative. It's the f prime of c in the model, but they actually said slope. So I'm just going to write slope equals 5x over y squared. To write the equation for the line, I need a point and a slope. Well, go get the slope. How? You don't even need to take a derivative. Yeah, just plug it in. Sometimes you'll need to take a derivative. Like on this one, I need to take a derivative. On your Delta math assignment, one of the kids had, because you get kind of different ones, but it actually said f prime of x equaled x plus 7. And they were trying to find the slope at 0. And somebody asked me, well, what's the slope at 0? I'm like, f prime of 0. What would it be? 7, right? But they were confused because they're used to finding the derivative. You know what I mean? So be careful. On this one, it was handed to me right here. This one, it's handed to me. This one, I'll need to find it. You need to be able to monitor and adjust. So on here, go ahead and tell me what the slope would be when you plug this stuff in. What's my slope I'll use? You guys go ahead, plug it in. What do you get? Bo, do the arithmetic for me. I'm too lazy. Yeah, you do. You can plug a 2 in here and a 6 down there. I hope. Sure, let's reduce that to what? Yeah, see, you do too. No, you never get by with I don't know in this class. All right, so there's my point and my slope. I'm not even going to look at what's in that box, Kellen, because I said I want you to avoid it. I just want you to use algebra 2. Let's just go do point slope form first. Y minus the y I know is equal to the slope there times x minus the x I know. And I basically, if this had been last chapter, I'd be done. That's the equation for the tangent line. Now I have to use it to estimate what happens on the actual curve. So here's where it changes. I told you make sure you now solve it for y. We haven't been doing that before. So just subtract that 6 over, right? So that's the first change. So just kind of note there's tiny little changes, but it's pretty easy to move a number over, right? The other little change is I said if it's not multiple choice, you really should name it. You should name it that this is the tangent line, or you could call it big L of x. So my tangent line is going to be used, and I'll do negative 6 plus 5/18 times x minus 2. What does the stem of the problem say I'm supposed to use it to do? Because now I'm going to use it. You're used to writing it. Now we're going to use it. Lizzie, what does it say? I'm supposed to use the equation for the tangent line to do what? Yeah, Yeah, to estimate f of 1.8. So I don't know what f was. I have no clue. I had some red function f. It sailed through the point 2, -6. I just hopped on and did a tangent line equation because they told me what the slope was. And I'm saying I'm going to go a little bit to the left of that, hop on the line and say, well, how close am I? So I would say f of 1.8 is approximately, and where do I put the 1.8? Into my line. Yeah, exactly. If you understand it conceptually, you shouldn't have to memorize anything. It's the equation for a line that you're actually going to use. So we'd have -6, plus 5/18 times, what would that be? -2/10. So I'm going to write it, I like fractions better. 1.8, -2/10. Let's do -1/5. That would be easier. All right, so I'm going to do a -1/5. You're going to get a lot of arithmetic with this stuff. So when I'm all done, it looks like I have a -6 minus 1/18. If you had to, Harvey, would you be able to write that as a single fraction? Yeah, I think we ought to at this age, so I'm not going to keep going with the arithmetic. All right, so what I want you to do is we're going to do one more together. Then we'll try one on your own, see how it goes, and maybe just bail. So let's go take a look at this one. This one's different because now I'm actually giving you a very specific function. And it says use a tangent line to this curve to approximate what happens at 1.5. Where do they say to hop on the curve? Because I've got some sine wave going on. It's got a vertical stretch and a whatever, but where am I supposed to hop on it? At pi/2. So let's suppose that this was at pi/2. I'm going to hop on there. I'm going to make a tangent line. All right? So I need a point. I'm not memorizing a model. My point is at pi/2, comma. They didn't hand me the y-coordinate. How do I get it? Just like we always have done it, right? Right, Harvey? Yeah, you plug it in. To what? The original function, you want to get on the curve. Some kids will find the derivative, plug it in there, and that tells me you don't get the concept. So we're going to go plug it in right here just to see where is that. Pi/2, and its sign would be 1. So at pi/2, comma 4 is my point of tangency. So you always need that first. Point of tangency. Pi/2, comma 4. What's the next thing you need? It's not new. I'm trying to make it not new, to be honest. It's new, but it's not new. I need the slope. Now, how do we get a slope? This one, it told me what to do. This one, it didn't. Take the derivative. Exactly. So my slope would be g prime. What's the derivative of sine? Cosine x, yep. And the derivative of 1 is 0. So how do I find my slope here? If you get the concept, it's easy math. How do I find the slope there? Plug what in? Plug what in? Pi/2. Into what? The derivative. Yeah, I want the slope. Excellent. So I do cosine pi/2, which is 0, boom, boom, boom. This tells me my slope there is 0. Actually, where does it tell me I am on that sine wave? Since my slope is 0. I'm at a top or a bottom, right? I didn't graph it, so I don't know yet. But I'm either at the top of one of these. I'd actually kind of maybe need to tilt that. It's at either one of those two peaks is my tangent line that I'm hopping on. So I need to write an equation for my tangent line. It goes something like this. I'm going to just keep working through this space. It says y minus the y I know is equal to the slope there times x minus the x I know. That was kind of a waste of time, correct? Because if it's horizontal through pi/2, comma 4, what's its equation? Y equals 4, yeah. So what I'm telling you is up at y equals 4, there is a horizontal tangent line that I'm using to approximate. All right, here we go. So the question is, this is where it helps to change the name. My tangent line, regardless of what x goes in, is 4. It's constant. Every y value, no matter where I am, 4, 4, 4, 4, 4, 4, 4, 4. So in particular, if I were using it to estimate what g of 1.5 is, I'd say, well, it's about 4. Right? So Christian, can you on your calculator actually go do it for me? Okay, so let's go answer this. He actually plugged it into the original 3.992. Now watch what this tells you. Your approximation is a little bit high, right? Which means your tangent line's above the curve. So was it a max or was it a min? It was a max, yeah, so I actually drew a decent picture not even really knowing that. And I have a little gap there when I was at 1.5 would be a little to the left. That difference between the two is the little gap between the line and the curve. Paige, does it make sense? Because if it does, they're easy. If not, you're going to go do the delta math and I'm going to have to come and help you. So, but I think I want to give you a ton of time to work today. So let's go take a look at this multiple choice one. Then I'll have you add one more thing to the bottom of your notes. Here it goes. It says, let h be a differentiable function such that h of 4 is 3. The derivative there is -2. Hello, they just handed me point slope. Very nice of them. If the tangent line at x equals 4 is used to approximate zeros. All right, so you have some function, and at 4, there's a tangent line that we're going to use to approximate the zeros. You need to know what a zero of a function is. What happens at a 0 for the function? It hits the x-axis. So what value is y? 0. It's important to know that the y is 0. So let's go start the process. You don't need to look at any sort of model. You're just going to go point, got it, slope, got it, algebra 2, love it, correct? Boom, nothing new. What did I say of the two new things? What did you say, Bo? Yes, solve for y, so we'll add the 3 on over. I also said to rename it if it's not multiple choice, but no one would know if you renamed this, Calvin, so I wouldn't waste brain power or lead doing it. So the question was, use it to approximate the zeros. So I want to know the x's when the y is 0. So all you're going to do is replace your y with a 0, and we'll go figure that out. We have 3 minus 2x plus 8. You guys go ahead and wrap that one up using the tangent line to approximate your zeros on F. And if this were an AP question, what do we got? 11 halves. So answer is, we don't have a calculator, so it's going to be C. So what I want you to do before we head on off to the assignment is go back up to this box, and in the bottom I want to make sure you understand that when you have something concave down and the tangent line then consequently lives above the curve, you will have overestimates. But remember, that's when your second derivative would be negative. Because it's concave down, you get overestimates. So when it talks about over or underestimates, you need a second derivative. That was messing kids up this morning in one of the Delta Math assignments. So the first person to get there is going to let me know, and we're going to do their first one in the second set. If I'm concave up, then when I hop on my tangent line, I'm going to be below the curve, so I'll have underestimates. What's got to be true about the second derivative right here? It is positive. So the question about over-underestimate is about the second derivative. All right, so for your homework, you've got two things that are going to happen. I'd like you to do the delta math first, though, before you do this AP assignment. You can get one or the other done in a half an hour, but I'd prefer you do the delta. I'm going to pass this out. If you're listening to these notes, I am passing out the worksheet on linear approximations and the key to it's in Schoology, so you can just use the key as your guide and do it on a separate sheet of paper. All right, so two things. Before you start, you can skip, there's 10 multiple choice on here, but we're going to skip 2 of them because we haven't covered the derivative of E. So number 6, you can cross out. I found this online and I love it because somebody actually took the time to go find old AP questions on tangent lines, but they have some stuff we haven't gotten to yet. 6 and 7 you can cross off. All right. But then don't start this. Some of you will finish the delta math in time to start this, but go to the delta math. The first set hasn't been an issue today. I've had to help a couple people, but the first person to successfully go to the set, there's 3 problems in one set and 3 in the other. And it's titled linear approximation. So 6 of them ideally if you get them right the first time, but I want the first person to hit the second set. We're all going to stop and do that person's first one together, because the second set, the first problem, kicked some people's butt this morning, and then they kept getting the red X, and then it's got a penalty, so I'm being nice to you guys. First person, second set. Let me know and we will do yours. Oh, I should take this off. He's not. What'd you say? So remember